G'day, in this video we're going to be looking at how to calculate the time of flight, maximum height, final velocity and horizontal range of a projectile. We're going to continue working through inquiry question 1, and the concepts that we look at today are going to help us to complete problem-solving style questions involving the motion of projectiles. So our key learning intentions today is to apply some of the basic principles that we've learnt so far about projectile motion to then be able to calculate for a variety of different values associated with the motion of a projectile. So they'll be time of flight, maximum height, final velocity, and horizontal range. So if we want to calculate the time of flight of a projectile, there are a couple of formulae that we need to take into consideration. First off, that Vy is equal to Uy plus Gt, and that Sy is equal to Uyt plus a half Gt square. Furthermore, a concept that we need to consider is the idea that the time of flight of a projectile is going to be equal to the time taken for the projectile to rise to its maximum height, plus the time taken from that projectile to then fall from maximum height back down to the ground. What this effectively means is when we're calculating for time of flight, we usually have to first calculate for these two values in order to then add them up and solve for time of flight as a total. In both of these calculations, we need to be reflecting on the motion of the object in the y-axis. When calculating for t rise, we're going to apply our formula Vy equals Uy plus Gt. When we're applying this formula, we're going to assume that when the projectile is ascending, when it reaches its maximum height, the velocity in the y-axis is going to be equal to 0. In other words, at that point of maximum height, the object is not moving in an upwards or a downwards direction. There is no velocity in the y-axis. If we are to substitute in 0 into our formula here for Vy, we just have 0 is equal to Uy plus Gt. If we rearrange for t, we can find that the time of rise is equal to negative Uy divided by G. This formula here will then allow us to calculate for the time taken to reach maximum height. Now, for a projectile that is launched from the ground, we can assume that t rise is going to be equal to t fall. In other words, the time taken to climb to maximum height is going to be equal to the time taken for it to fall back to the ground. However, as we start to look at some more complicated problems where an object is not being launched from the ground, calculating the time of fall is going to require some additional problem solving. In this scenario, we need to be focused on the idea that Uy is equal to 0. In other words, when we're at the maximum height, the starting velocity in the y-axis will be equal to 0 before it begins to start to fall back down to the ground and build velocity in the negative direction. Assuming that we know the displacement in the y-axis, in other words, how high the object actually is, its maximum height, we can apply the formula Sy equals Uyt plus a half Gt square, eliminate the U term because Uy is equal to 0, meaning that Sy is just equal to a half Gt squared, and we can rearrange to find the formula here that the time of fall is equal to the square root of 2 times Sy over G. Now, in our practice question, when we're looking at our ball being thrown, we are going to assume that the time of rise is equal to the time of fall. So in this solution, we're going to first calculate the time for the projectile to rise, and then from there it'll be very simple math to calculate the time of fall and therefore the time of flight. So to solve for t rise, again, we're using our formula Vy equals Uy plus Gt, and running with the assumption that once we get our projectile up to the maximum height, the velocity in the y-axis is equal to 0. We can substitute that value in, rearrange our equation, and we get that the time of rise is equal to negative Uy on G. If we substitute our relevant numbers into this equation, we end up with a value which is 1.9 seconds. Now, if we're running with the assumption that the ball is being thrown essentially from the ground up into the air and back down to the ground again, and sort of divide our parabola up into two parts. We have the ball traveling where we have t rise. We have the ball traveling until it hits the ground again, and then we have t fall. And the assumption that we'll have here is that t rise is equal to t fall. the time it takes for the ball to get from its maximum y velocity when it's launched to its velocity of 0 when it gets to the top is going to be the same as the time taken for it to get to velocity equals 0 at the top to hitting the ground back down at the bottom. Now, if this is the case, we'll say that the time of flight, which is a total, is going to be equal to 2 times the time of the rise, which is equal to 2 times 1.9 seconds, which is approximately equal to 3.8 seconds. And there we go, we have our time of flight. This value is actually going to be really important for some of our other calculations to follow in this video. Next, I want to show you how to calculate maximum height for a projectile. Again, some of our key kinematic equations are going to be really important. Because we're talking about maximum height, we're going to be analyzing the motion of the projectile in the y-axis specifically. Again, because we're analyzing the projectile at its maximum height, we're going to assume that the velocity in the y direction at this point is equal to 0. Therefore, again, we can calculate for t-rise. Technically, we did that in the previous question. So if you've already calculated the time of rise, you don't have to do it a second time. But when you do calculate for the height of a projectile, you will need to know the time taken for the projectile to get from where it was launched to its maximum height. From this point, we can substitute t-rise into our s equals ut plus half at square formula to calculate for the displacement in the y-axis that the projectile actually undergoes. Something to keep in mind here is if we are completing a question, and we're not going to do one of these today, but we will do some eventually. But if we do get a question where the object is being launched from a height above the ground level, the maximum height is going to be your SY value that you calculate with your kinematic formula. But that's going to tell you the height from launch point to the maximum peak. The launch height is also going to be a factor that you need to take into account. So for example, in our ball example, if we were to throw that off a 5-meter cliff, not only would you be calculating for the maximum height, but you'd also be accounting for the 5-meter cliff, which is below it. That would be equal to the maximum height of the projectile. So in our practice question, again, we have our same ball. It's being thrown at an angle of 48 degrees at a velocity of 25 meters. In this question, we need to find the maximum height of the ball. So for this question, there's only 2 variables that we need to take into account to calculate for the maximum displacement. There's uy, which we've already calculated in our initial velocity question in the previous video. We also need t-rise, and from the previous question in this video, we found that t-rise was equal to 1.9 seconds. From here, we can just substitute in all of our values to calculate for S max, which is our maximum displacement in the y-axis. This gives us a value of about 17.7 meters or 18 meters to 2 significant figures. 2 more variables to go. We're now going to look at how we can calculate the velocity, the final velocity for a projectile. In order to do this, you're going to have to first be able to calculate Vy as well as Vx. Once we have those 2 values, if we know the final velocity in the y and x axis, we can do a vector sum to give us the final vector for that final velocity. So for the y-axis, we're going to use 2 key equations, our s equals ut plus a half at square formula. First off, to find the time of fall if we haven't done so already. Again, if you already know the time of fall, then you don't have to use this formula. But if you do a bit of a rearrange and assume that the initial velocity as the projectile starts to fall, in other words, at maximum height, is equal to 0, you can sub that in and you'll end up with S max is equal to a half GT squared, rearrange, all that kind of stuff, and you'll end up with this formula, just as we looked at previously. Essentially, if you are able to find the time of fall, we can sub in values here to be able to calculate for the final velocity in the y-axis. As for the x-axis, this process is a little bit easier. As we've talked about previously, we assume that acceleration in the x-axis is equal to 0. Therefore, when we apply the v equals u plus at formula, the at term gets completely cancelled out, meaning that the final velocity in the x-axis is going to be exactly the same as the initial velocity that we started with in the horizontal to begin with. Let's have a look at trying to apply that to our key practice question here. What we're going to calculate here for first is the velocity in the x-axis at t is equal to 1.9 seconds. In other words, after the object has fallen from its maximum height back down to the ground in that 1.9 second period, which we determined in a previous question in this video. We're also going to assume that ax is equal to 0. And in doing so, we can calculate for Vx at t is equal to 1.9 seconds. In other words, the final velocity in that x-axis. We know that it's equal to ux plus ax t. In fact, what's interesting, as we talked about before, is that time doesn't matter because ax is automatically equal to 0, which means the velocity in the x-axis at the very end is just simply going to be equal to ux. We're also going to calculate for the velocity in the y-axis direction at t is equal to 1.9 seconds. And we know that that is going to be equal to, again, uy plus gt. We can assume that at max height, uy will be equal to 0 because at maximum height, there is no velocity for the projectile in the vertical direction. And as a result, our final velocity in the y direction at t equals 1.9 seconds is going to be equal to simply gt, or g times the time of fall. This is equal to negative 9.8 times 1.9, which comes out to about negative 19 meters per second. Note that this value is negative, which means that the vector in the y-axis is going to point downwards. So we can start to find this by doing a vector sum first. Now to calculate for v, we can first do some Pythagoras to determine the magnitude of the vector. Then we can do some right-angled trigonometry to calculate for theta, the angle that's going to describe the bearing of the vector. Note too that when I do substitute in my velocities of 17 and 19 meters per second respectively, I am going to be substituting in non-rounded values which I've been saving in my calculator as we've moved along and done these calculations. Note here that the vector for the final velocity of the projectile is essentially equivalent to the initial velocity of the projectile. We just have the velocity vector pointing below the horizontal instead of above it. This is to be expected because of the symmetry that we see in the equations, as well as the parabolic motion of the projectile as it moves through the air. Again, there will be some additional complexity that we start to see in questions like this if we begin to introduce scenarios and concepts where potentially there is a different launch height, which begins to make our parabola asymmetrical in a way. The last thing that I want to look at today is how to calculate the horizontal range for a projectile. Essentially, to do that, we need a displacement value, and we know that S is equal to ut plus a half at squared. This formula is really easy to apply because, as usual, in the x direction, we can completely remove the second term that has the acceleration in it because we can assume that there is no acceleration in the y-axis. As a result, the distance that is travelled by the projectile in the x direction is simply going to be equal to the initial velocity times t, or in this case, the time of flight. So for our running practice question, again, we assume that ax is going to be equal to 0. So if sx is equal to ux t flight times 1 over 2 at square, and that gets completely cancelled out, then we can say that sx is equal to ux times t flight only. Which means all we need to do is substitute in our values and spit out a number at the end. So ux, as it was at the beginning, is about 17 meters per second. Note that when I do calculate this, I will be substituting in the unrounded value, but the time of flight as well is about 3.8 seconds. Again, I'll sub in the rounded value from my calculator. But when you do multiply these two values together, you should get about 63 meters. So what this means is that the projectile will be traveling 63 meters from start to finish as it makes its way to wherever it lands. Thank you very much. In the next video, we're going to be looking at how we can observe and measure variables for a real projectile in motion. And these activities will get us set up to be able to complete some practical work on this inquiry question. But until then, have a good one.